Now let's recap some machine learning fundamentals. For example, what is machine learning? Well, machine learning is a discipline that uses statistical methods to progressively improve from previous information the performance of an algorithm, what we call a model, in a given task. So now you can understand why we have studied statistics before this last course. A machine learning model is able to learn, and in the next section we will characterize in a mathematical way the concept of learning, from data in order to perform a given task in the best possible way. So again, let's repeat, the three key elements of a machine learning model are data, learning, and task. And let's start with the first one, with briefly recap those concepts. So the first key element is the data, and the data is the information. And now we know that data can be described using random variables. In a tabular data, every column can be described as a random variable, a numerical or a categorical random variable. But thanks to the new type of algorithms, we could feed to the machine learning models with images, audio, or text. We just have to pre-process that inputs in such a way that every input becomes a number, and then the model can deal with, because the model can deal only with numbers. The other key element about data, is the fact that you don't know how much data you will need if you don't know the difficulty of the task and the algorithm that you are going to use. Some algorithms require more data to work well, and also if the task is not that difficult, you probably do not need a lot of data. So it depends on the task and on the algorithm you choose. Of course, if the task is easy, you don't want to use very complex algorithms that are very data hungry. The second key element of a machine learning model is the learning. And here we will take a general overview, a very abstract overview, and in the next section we will cover with notations, with expressions, mathematical expression, what this means. But remember that a model learns when it changes its structure, its parameters, to reduce the error of the outputs. For example, here we are talking about parameters. So the model, when it learns, it adjusts its parameters. This could be seen as an estimator. So a machine learning model is a particular type of estimator, which uses the process of learning to estimate those parameters, the parameters that allow him to describe the random variable that generates the phenomenon of interest. And the learning could be of three types: the reinforcement learning, the supervised learning, and the unsupervised learning. In the reinforcement learning, the machine learning model is called agent, and the data is collected from an environment. In reinforcement learning, the model can take what is called an action and gives and the environment returns back to him a reward and a state update of the environment. So the agent here in reinforcement learning interacts with the environment and interacts trying to maximize the obtained rewards. And the process usually is a trial and error process. In supervised learning, instead, the machine learning model suffers the environment, is passive, but is trained to output a prediction. So the model here aims to predict the behavior of one or more observed random variables with respect to the others. So we have a set of data, a multidimensional random variable, and we feed that data to a machine learning model which aims to predict the behavior of another random variable. In supervised learning, learning is informally supervised by the ground truth values, and the ground truth values are the observed values for the random variable we are trying to predict. In unsupervised learning, the model still suffers the environment, but now it does not output a prediction. So the model aims to find patterns and links between the data. So in here we do not have two random variables, the data and the random variable we are trying to predict the behavior, but we have on hand just the multidimensional random variable that describes the data. And what we want to do? We want to understand how each column, for example, in tabular data, is related to each other. The third key element of a machine learning model is the task. And the task defines what the model is trained on and with what intentions. So we have two cases. When we get a set of data, we could extract some random variables called target or response variables, and this could be intended as more important than the others, the features. In another case, all variables are intended as potentially significant. So given a set of data, a multidimensional random variable, is up to us, to the observer, to decide how we intend to interpret this information, and whether to assign particular importance to any of the available random variables, any of the columns in our tabular data, for example. And also, we can link the two cases with some particular tasks. When we interpret a target variable inside our data, then we are talking about regression if the random variable we are trying to predict is continuous, or classification if that random variable is discrete. If all variables are intended as all potentially significant, then what we are aiming to do is a pattern discovery task, for example, clustering. So wrapping up how our machine learning models work. We start from data, and from this set of random variables, we define a task. For example, could be supervised learning. And depending on the task, we can use only a particular set of machine learning models. We choose one, and we start to train the model on the data through an iterative learning process. Then, when finally the performance of the model are at its maximum, then we can take the model and put, for example, on production and get some output of this machine learning model. For example, in the case of supervised learning, this output will be a prediction. Now, in the next section, we will characterize in a formal way the supervised problem. Okay, let's focus on supervised learning. And in this section, we will see through math how real world meets mathematical abstraction. And by mathematical abstraction, I mean what we have studied in the statistics course. So again, machine learning and data science are about understanding a phenomenon and taking advantage of it. But how we can understand the phenomenon? Well, nothing is sure in life, so it needs to be treated with probabilities. Again, we link this content to the course of statistics. And this is how we see the phenomenon. This picture should be already familiar to you. The population, the sample space is where the phenomenon lives, but we get only a limited set of samples from all the outputs that that phenomenon could output to us, and this is the output sample. So our goal, uh, the so the phenomenon is seen from the population to the observed sample through a sampling scheme. And our goal is to use statistical inference to explain the phenomenon in the more general way possible, which is by finding some rules that are true for each element of the sample space or maybe the population. How we do statistical inference? Well, we will use a machine learning model, a particular type of statistical model. In supervised learning problem, let's start by defining the dataset. Our observed sample is called dataset. In here, we are doing a regression task. So we get our set of features, and here we'll consider only a one random variable, which will be our target variable. How many observations do we have? N observations. But how we can describe the machine learning model? Well, every phenomenon has a deterministic component and a stochastic component. In some way, the stochastic component could be seen as the randomness that cannot be explained but by the machine learning model. In fact, the machine learning model here is this function f that takes the input as input the features and outputs a sort of prediction that is deterministic. And then we say that adding this deterministic output to some stochastic, some randomness, we get the real observation. The model is a parametric model, so yes, it takes the features as inputs, but as some settings inside it, which are described as parameters. Then, finally, we have to describe the task of our supervised learning problem, our training objective. And in order to do so, we have to describe a particular function called loss function. In here, the loss function takes two inputs from the target variable domain and outputs a real number. What is the meaning of the loss function? Well, we take the predicted value from the machine learning model and the real value we have observed, and we can compute a loss, a sort of error between the prediction and what we have really observed. Here the loss function is computed event by event, observation by observation. So we have we can apply the loss function for each of these elements in the dataset. But what we are trying to do? we wish to reduce the total error produced by the model over the whole dataset. So the loss function is not enough here, because it's computed between only with the information of 1 point. In order to compute some sort of error with the whole dataset, we define the risk function. And the risk function is the expected value of the loss function computed between the machine learning model and the observed values of the target variable. Here is the abstract definition, because since we are defining the expected value, it means that we have to compute the expected value onto the sample space. But we do not have the complete access to the population, to the sample space. We are building the machine learning model because we do not have that access. So we need to approximate that risk function in order to be able to train the machine learning model. And this can be done by introducing what will be called the empirical risk function. So let's take a deeper look to the definition of risk function here as expected value. We are computing the integral on omega, which is our sample space, and what we do here is we use the cumulative distribution function. But here is the abstract cumulative distribution function, the true one. But we do not have access to this, and we have to approximate the distribution. We can do this by defining this sort of empirical cumulative distribution function, in which this I means that it takes value 1 only for x less or equal to xi and y less equal than yi. In the left picture makes it more clear. On the right side we have the empirical cumulative distribution function. For example, here we are taking the sum of all the elements between here. So this is a monotonic function that increases while I increases. And this is the probability distribution function. An histogram, that's what we have, taking a look to the observed sample. So now, through the definition of empirical cumulative distribution function, we can approximate the risk function with the empirical risk function. That is a function not only of the parameters of the machine learning model, but also is a function of the dataset. Because of course we have built the histogram taking into account that specific dataset. So since this is equal to 1 only when these two conditions are true, then we get that the empirical risk function is the simple loss function average computed on the training data, the dataset here. But we will characterize more while in the next section while we are talking about training data here. Some examples of empirical risk function could be the mean square error, in which the loss function here is the square error. And since the empirical risk function is the average, the mean of the loss function, we get the mean squared error. Another type of empirical risk function could be the mean absolute error. Usually these two metrics are used in with a continuous target variable, and the mean square error is often used. When dealing with binary target variable instead, we have the binary log loss or cross entropy. And if you remember correctly, here we are looking at the loss function. We just have to characterize its empirical risk function. We have just to take the average of this loss. But here you can see, if you remember from the previous course, that this is the log likelihood function for a binary random variable, which means for a Bernoulli distributed random variable. So I've said previously that the empirical risk minimization is the foundation of the machine learning theory. Well, because the empirical minimization theory explains how a machine learning model is trained through this formula. The goal is to estimate the parameters of the model by minimizing the risk function, which depends on the task, because we choose a proper loss function from the selected task. It depends from the model, because we are computing the loss function between the model and its parameters, and the observed values of the target variable, and is also a function of the observed sample, the data, because the definition of risk function is a function of the observed sample. So training here in machine learning means that the model simply refers to finding the optimal, since this is an optimization problem, parameter values. How we can find those parameters? Well, we know that if this theta hat is a minimum for the risk function, then also the gradient of the risk function in that point would be 0. But this is the inverse is not always true. For example, if we take a look to the right expression, theta hat could be a maximum, a saddle point, and still have the gradient of the risk function equal to 0. But the idea here is to try to go from the right to the left by designing some algorithms that are able to discard the saddle points and the maximum, and, if possible, the local minimum. We would like to reach the absolute minimum, which guarantees to us the absolute minimum risk function, the minimum error of the model through the data we have on hand. Again, when going from right to left, we need to avoid saddle points and avoid, or maybe escape, from local minimum. What does it mean, computing the gradient of the risk function? Well, here it means that we are, of course, focusing on the empirical risk function, but the empirical risk function is just an average. So since the derivatives, the partial derivatives, are a linear transformation, the differentiation of the sum is the sum of the differentiation. So we get the average of the gradient of the loss function. But usually the loss function is simple, so we can compute the partial derivative of the loss function with respect to the model, and then finally compute the gradient of the model with respect to its parameters. This right term here is the one that requires the more effort, because the loss function you have seen is very simple to compute the derivative onto the loss function. So let's look at an example. A model with two parameters with a mean square error risk function. Mean square error risk function means that we have this risk function here. In the next slides here we will not explicit the fact that this risk function is an empirical risk function. And since we are considering a model with two parameters, our theta hat would be a vector of two components. Our optimization problems means that we have to compute the partial derivatives with respect to the two parameters and search the values of the parameters such that the partial derivatives are equal to 0. We will consider the first line here, the parameter theta1. In the next slides. Again, we take this term, we will refer to this risk function. What it means? It means that we have to compute this partial derivative. We already know and we can apply derivatives such that applying the chain rule, the derivative of a of bx squared is equal to these terms. This computation is useful because now we can compute the derivative with respect to theta1 onto this squared term, and we get that our problem resolves to the fact that we have to 2 over n sum between 1 to n of ya minus the machine learning model output times the derivative of ya minus the output of the machine learning model. This simplifies because ya does not depend on the parameter. So here we have this simple expression and finally the derivative of the model with respect to one parameter. And now let's move on looking at a practical example using linear regression. What does it mean, linear regression? We take the risk function as the mean square error. Here we use the notation that is almost always used when dealing with a machine learning model. In fact, for example, when programming a machine learning model, this expression is not called risk function, but I would say in an improper way, is still called loss or error function. So we get the data. Here we have just one feature and just one target variable. We have our loss function. Again, it's in reality is a risk function. We described our model, which is a regression model, a linear regression model, so it has two parameters, so since this is just only one feature. And the algorithm, the goal of the algorithm is to search for the parameters that allow, the parameters values of course, that allows to minimize the loss or error function computed on the known data, the observed data. And this is the process of learning. You see that through iterations, the model gets better and better and better and fits more the data. In fact, we are in a supervised learning problem, and these are the predictions, outputs of the machine learning model. So, looking back to the formulas, the risk minimization, let's compute the risk minimization with respect to a linear function, a linear regression model. In here, we described the machine learning model as θ1 times the feature plus θ2. So, remembering this is the expression of the optimization problem for a two parameters model, then we just have to substitute this inside here and here. And the partial derivative with respect to the linear model is pretty straightforward, because here only the first term depends on θ1, and also the derivative of θ1 is equal to 1, but we have a scalar multiplication here, so is equal this operation is equal to xi. So again, let's keep the model in a more abstract way, and we get xy here in here. So solving for both the parameters, we get two equations, of course, one for each of the parameters, in two unknown variables. In particular, with linear regression, we can get exact solutions. But in general, it's not necessary. It's necessary to implement iterative algorithms to get some solutions to this system of linear equations. And in particular, that algorithms need to be able to find good solutions for the optimization problem. And by good solutions, we mean that the algorithm must not get stuck on local minimum or saddle points, but has to find the global minimum. Again, here we have seen how through iterations the parameters change to better fit the data, the relationship that can be observed between the features and the target variable. So learning here is about finding the best model parameters. But there are particular machine learning models, the deep neural networks, that are very powerful, but require a lot of parameters. For example, deep neural networks are the most powerful tool when used when we want to solve image, text, audio related problems. There are several types of architectures of neural networks. For example, the multi-layer perceptron on the left side, the recurrent neural network here in the middle, the convolutional neural network on the bottom, and on the right we have the transformer, the new one, one of the new architectures of neural networks. So, especially in neural networks, the model can have millions of parameters, so searching for their values that minimize the loss function becomes very complex. For example, here we have a loss surface, what is called to be a loss surface as a function of two model parameters. For example, a linear regression model could have this loss function surface. Again, here we use the term loss, as in a machine learning model is said to be, but we are referring to the risk function, empirical risk function. So in here, the z-axis is the risk function with respect to the x and y axis, which are the values taken by the parameters, by the two parameters. So imagine this with, or maybe we cannot imagine because we are human, this is a 3D space with two parameters. Imagine what would be a space with millions of parameters. That's the context of an empirical minimization theory should work. And in neural networks, the optimization process is done via backpropagation, as we have seen in one of the previous courses. So the development of a powerful optimization through algorithm here is crucial because allow us to find the best possible solution. For example, here these balls are attached to different optimization algorithms, and the algorithms of that bring the balls to this local minimum are the worst algorithm possible. We want optimization algorithms that are able to find the global minimum of the loss surface. One of the most popular basic optimization algorithms, because this algorithm then is evolved in a more complex way, is the gradient descent algorithm, in which for each training iteration, the parameters are updated in this way. We take the parameters in now, and we subtract the gradient of the risk empirical risk function times a scalar, a number, eta. And this will be the new set of parameters. And the algorithm is stopped when the the parameters of the previous iteration and the new one are almost approximately the same. Why? Because this means that the gradient is approximately null. So we are in a minimum. Could be a local or an absolute minimum. Why am I sure that this would be a minimum and not a maximum? Because of this sign. And this number here is called learning rate. So we are applying our learning rate to the gradient of the empirical risk function to adapt the parameters. And again, here the gradient can be exploded in the two components, and as you can see, is used as the direction of the steepest descent, because here we have the minus. So we are taking the descent of the algorithm. That's why it's called gradient descent algorithm. But taking, for example, the several versions, a complex version of the gradient descent algorithm, we have to judge those algorithms. And the two ways we can, the two properties that an optimization algorithm should have are the convergence speed should be as fast as possible to converge at local or better an absolute minimum. And the second is to the accuracy of finding the global minimum. So we want an algorithm that is very fast in finding the minimum, and also we would prefer that the percentage of finding the global minimum is at its maximum. So again, here you can see that these algorithms are very bad because the balls stop at a local minimum, but also the algorithm that is used with this green and white ball are also bad. Why? Because yes, they bring the ball to the global minimum, but they are very slow, so the convergence speed is very low here. But some machine learning models are more complex than what we have seen so far. Right now we have seen that the machine learning model is a function which has some parameters in it. But usually the machine learning models have, other than the parameters, some hyperparameters values. These hyperparameters could relate to the way we train the machine learning model. For example, here you can see the learning rate is an hyperparameter, or could be some settings of the model inside it. For example, the penalty or other here. So why we distinguish between parameters and hyperparameters? Well, parameters are learned from the machine learning model through the optimization process. Hyperparameters are settings, are model or training settings that are not learned from the optimization problem, but instead are required as user input before the training starts. Here, for example, we have the learning rate. We can see the behavior of the learning rate, which is an hyperparameter in linear regression. The linear regression is always the same. It requires only two parameters, as we have seen before. But here, the different learning rate changes the way the model adapts to the data. In this case, adapts in a poorly way. We have to find a better learning rate here. For example, the learning rate is very important because if it's too low, so the steps are very close one to each other, then the optimization algorithm could stop on a local minimum. That's because the steps are so close one to each other, then when the ball here, the algorithm, gets into a local minimum, it cannot get out from it. The steps are too close, are too small. If we take a learning rate too high, then the algorithm cannot find the best parameters here, because it keeps jumping from one point in the loss surface to the other, but it gets not at its minimum. So the goal when training a machine learning algorithm that requires a learning rate is to find the best possible learning rate that guarantees to us to overcome local minimum, but also to reach the global ones. In order, through the training process, the algorithm, for example, the gradient descent algorithm finds the best parameters. We need another process before it to find the best possible hyperparameters. And this is called hyperparameter optimization problem. Again, in the hyperparameter optimization problem, we aim to find the best hyperparameters values such that the model can reach the minimum of the risk function by finding the appropriate parameter values. So for example, this is a neural network, a particular machine learning model. Here, the hidden layer could be, is actually a hyperparameter and determines also the dimension of the model itself. So when training a neural network, we have to define a set of hyperparameters. The number of layers, the hidden layers here, could be more than one. Number of neurons, which are those units, those circles, how many we want. And then the learning rate. We define these hyperparameters and then we train the model by finding the optimum weights. And then we get a score, a value for the empirical risk function. Then we try another set of hyperparameters, we train the model, and we get a score, and so on. We collect a set of scores, and the best hyperparameters will be the set that guarantees to us the best possible score here, the best performances. There are several types of algorithms to solve these optimization problems. For example, the grid search, the random search, the evolutionary optimization, and the Bayesian optimization. So, since now we have learned how to train a machine learning model, but now we want to be sure that that model trained on the observed observed sample would have good performance when put on production with unseen data.